Welcome back. I've got in today's video I have all the examples so far we've had fairly basic circuits. In today's video we have a slightly more complicated circuit, not too complicated, shouldn't take too long, but we do have a slightly more involved circuit to connect, including having to route some analog signals, having to do some power, having to just general op-amp considerations as well. And also having large pots that have to be accessible off board. So there's going to be a little more design considerations in the video today. I hope it helps just kind of going through. This isn't the only way to do it, but just see sort of how I would do a board like this. You might want to, when you watch this, watch it fairly fast, at sort of accelerated speed. I know a lot of people who do these kinds of routing and layout videos, they accelerate the video, but YouTube lets you accelerate the video, so feel free to jump it to ×2 or to whatever just to speed it up. If it might get kind of long and boring in parts. So I'm going to go over sort of what I'm going to be showing today. So this board is it is a board that receives a signal from a preamplified acoustic microphone, and I already sort of did the schematic here for this, but it basically takes. So you'll notice, you might recognize this connector from the previous acoustic amp preamplifier, where it's got a positive 12 rail, negative 12 rail, signal rail, ground. This board also has, so this is the power that's going out to that external preamplifier and the signal that's coming back from that preamplifier. So what we're doing here is we're taking that preamplified signal, we're taking it through one more round of amplification. And in this case, this additional round of amplification, we have a pot here so we can adjust the gain. It's at least somewhere where we have in this path that we can adjust the gain to sort of get the levels we need. We also have this op-amp circuit here. You'll see it has a diode at the output. That's a good way to halfway rectify the signal. So the signal is coming in. It is capacitively coupled here, which is going to remove any DC that might still be there. There shouldn't be any DC, but it'll remove any little bit of DC that's there. And then it amplifies it a little bit, an adjustable amplification. It halfway rectifies that signal, so now we should only have a greater than 0 signal after this. Then it runs that halfway rectified signal through a little bit, just a simple low-pass filter here. So this simple R4C2 is a simple low-pass filter. And then this op-amp here will take that, and it will essentially there is an adjustable threshold, and if the magnitude of that signal, and the magnitude of that signal corresponds to the magnitude of the AC oscillation here. If the magnitude of that signal is greater than a certain threshold, which is set using this voltage divider, through this potentiometer voltage divider, then it will sort of rail this op-amp to either 5 or 0. If the signal is less than that, it will rail the op-amp to 0. So it's basically a, so if the signal is higher than this threshold, rails to 5, lower rails to 0. We really should, so this is kind of digitizing the signal, using an op-amp to do it. There's better ways to do it, so we don't have to use an op-amp. We could use a voltage detector. There's a comparator would probably be a better way to do it. Probably running it through digital logic we should do, but it should work fine for this. It should work fine producing a digital signal. The op-amp that we're using has a pretty good slew rate, so it's going to be a fairly clean edge when it does this. It's not too much to worry about. But just note that maybe we should have added an extra kind of Schmidt trigger buffer or something like that to clean this signal up. So we also have that signal though, so now this is the rectified sinusoid, which has been low-pass filtered, so it should kind of be just sort of a DC with ripple, where the magnitude of the DC corresponds to the amplitude of the AC. That then runs through this circuit here. This circuit here is, this is an integrator. So we have an integrator, it's a leaky integrator here. So that is going to, so basically this circuit here gives you a digital yes-no if our signal at any moment in time is exceeding a threshold. This then integrates that analog signal, and it looks at and it's a leaky integral, so the integral value that accumulates will leak out. So this sort of gives you the larger the signal is, the larger this integrated value is going to reach. The larger this integrated value reaches, the longer sorry, the larger this integrated value reaches, the longer this pulse is going to be. So essentially we have one signal coming out of this, which is a pulse which says, is at this immediate moment in time, is the signal I'm getting from this hydrophone, does it exceed my threshold? The second one says, does the signal at, not only does it exceed my threshold, but based on how large the amplitude of that signal is, we're going to get a longer pulse coming from this second signal. So it's kind of a two-part system that that looks at the immediate value of the sample and also the magnitude of the sample. So it's kind of a digital. The second signal is sort of a pulse width modulation, which tells you the amplitude of your signal, and then the first pulse out here is just telling you, do I have a signal or do I not have a signal? So, and then there's processing later on. There's digital processing later on that's going to sort of take these pulses and sort of interpret them to mean various things. So we have to route this, but I want to point out one thing that I did here. So this is op amp here. We have U1A and U2A here. So these two op amps are actually on two separate physical packages, even though they're kind of the first stage of this amplification. These two op amps are U1B and U2B. These are on two physically separate op amp packages, even though they're in the same segment of this amplification. So why might we want to do that? So it's kind of hard to see because I didn't do a really clean job of doing the schematic. But why might we want to do that in this case? And maybe look at it for a few seconds and think about that. I know I'm switching into professor mode here instead of YouTube video maker mode here. But why, that normally doesn't make any sense, right? We have two op amps in the package, might as well use those two for this stage and this stage. One thing to note is, and it's one of the things that I don't like about the way we present packages here, is that this pin here, this pin 8 on this op amp, and this pin 8 on this op amp, these are actually the same pin. So they're the same pin on the same physical package, which means we should have the exact same signal connected to these. The problem is, this op amp here, I wanted to connect 5 volts and ground. It's a rail-to-rail op amp. I wanted this to be powered 5 to ground, so it rails at 5 to ground over here to sort of simulate a digital signal. And these I wanted powered plus 12 to negative 12 because that is the same range that our pre-amplified signal is going to have. So in order to get if I want to have this sort of high differential rail power for the op amps that are processing this analog signal, and I want to have this different 5 volts and ground sort of digital rail for my op amps that are going to be digitizing this analog signal, I have to do them on two separate physical packages because both op amps on the same package have to have the same power supply. So that's why we did that, in case it causes any question, just sort of a general op amp design principle. Okay, so the other thing I did, and you might notice this, is this op amp pathway sort of goes left to right, which is pretty common for when you have a signal chain that you're processing, signal conditioning on a signal chain. But one thing I like to do sometimes when that's the case is if we go to annotation, I annotated this guy down then across. So my order of processing was down then across. And the reason for that is because that helps me get all of these, all of the parts that are connected to this op amp, and they should kind of all be in the same physical location. These are going to be R1, R2, R3, R4, right? They're all going to have numberings that are sort of related to each other. And it's just going to make it easier to sort of connect these different parts, annotated parts, to sort of where they are logically in the circuit here. So this guy has, well, not a lot of components on this guy over here. But you just sort of see, right? If the component flow is left to right, then typically we want our annotation to be from left to right also. So that's one thing we did. Some people don't. Some businesses have standards for doing schematics and for doing annotation that say, no, use one technique and only one technique. Some also have, and sometimes the reason they do that is because they like to identify which quadrant the part is in. So they want to know, right? They want to make sure that quadrant A1 has the smaller numbered parts, A2 has slightly more, B1 has sort of those higher. So sometimes they want that sort of left to right, top to bottom approach in order to sort of keep these regions of the schematic sort of relatively reasonable. In this case, I guess the way we did it here, it would go from 1A to 1, D, and then from 2A to 2D, etc. And that would be the order that we would be numbering parts. Okay, I've talked too much. Let's actually start routing this thing. So I already, well, I just want to make sure. Oh, no differences. Okay. So I already moved all this stuff over to the PCB here. So the biggest thing you can tell, the biggest thing is these pots. So we're using multi-turn pots. And, you know, in this case, when you don't have a pot where it actually, somebody's actually going to be adjusting this. In this case, somebody's going to be adjusting this while out on a kayak on the water. We probably don't want we don't want to use a flimsy pot. We want to have something where it's a nice high quality pot where they're going to feel some resistance when they turn it, where it's going to stay in place when it's not being touched. We don't want it to be bumped and sort of shifted. And we want it to be multi-turn. We want to have fine control over this thing. So we don't want to use those sort of standard surface mount pots where you can sort of turn it 270 degrees or something. So we're using one of these multi-turn pots. And let's, you know, the good thing is we can sort of see the order of these, even though these are backwards. We know VR1 is going to be sort of the pot for the stuff further on the left, VR2 is in the middle, VR3 is on the right. So we should be able to order these fairly easily. One thing I like to do, you know, we're at the stage now where we're just trying to get these parts onto the board. We're just trying to sort of roughly get a shape for this board. And a lot of times what I like to do is I don't want to box myself in right now. I don't want to set a size of a board because I don't really know how big this board's going to have to be. But maybe what I can do is I can kind of be a little reasonable and I can move the big stuff into position and maybe give me one board edge. So maybe I'll produce one board edge and just use that board edge for now as a reference, and then I can start adding the other sides of the board later on. So this board is going to be vertical, so the pots are going to sort of come off the edge, and that edge is going to be vertical when it's actually being used. The connections to the hydrophone preamplifier are going to be off on the side. So we're going to start by basically putting these pots on the bottom edge of the board. And before we do that, I'm just going to place, so I'm going to switch my layer to keep out, if I can, place a line. And once again, it doesn't like me to do a line with keep out, so whatever. We'll do mechanical 3. Sometimes it's my default. Okay, and so I don't really care where this line is, how long it is. I just want to make a line. And this is going to be my reference. This is going to be my board edge reference, just for while I'm doing this part of it. So I'm going to move. The other thing I'm going to do is I'm going to set my grid very, very coarse. So 100 mil.
How do we tell that, or it doesn't matter?
This looks pretty good.
Yeah.
Okay, so we'll do VR1 there. VR2. Let's do it. 100 mil, 200 mil, 300 mil, 400 mil, 500 mil. Perfect. Looking good. Okay, so now we might want to change this later on. We might want to have, let's take a peek and just make sure these guys are on the top side of the board. They are. Okay. So we might actually want to space these out more if we can fit the electronics in between these. That actually might work really well. We'll just kind of have to see how it goes. In fact, actually, I think I kind of want to. Okay, move those guys a little bit more. So I know my connection to that ultrasonic microphone is going to have that, so that hydrophone is going to have to be here. So I'm going to, on the sort of on this edge of the board. So I'm going to put that here-ish, just roughly placing it for now. And you know, maybe we're going to want to have this guy on the other side. This is the power and power coming into our board here. Maybe we want this guy sort of on the other side. And again, we can move that around later. Okay, so let's start putting our op amps into place here. Now one thing is, this op amp is, remember, U1 is going to cover U1 is actually this amplifier and this amplifier right here. So it's kind of a little bit weird. But if I had to put it anywhere, oops, look at that, don't want to do that. So if I had to put it anywhere though, I'll probably put it between these two pots here. U2, we'll put it in here-ish. And maybe I want to, my grid is maybe a little bit too coarse right now. 25 mil maybe looks a little better. Now at the end of the day, we don't want this to be too tight, right? There's not really a huge space concern for this. This is going to be, you know, space isn't really a concern. The bigger concern is making it tough for people to sort of get in here and change these values, especially with these big pots here. I don't want, if we have to resolder, I don't want to have to sort of squeeze in here, so I'll probably fiddle with this thing a little bit more later. Maybe move these guys sideways, actually. That might be good. Good. Okay, now let's start piecing these components together. So let's get maybe R1 and R2 just near here. Let's get, looks like R3 and R4 also have to be near here. R3, R4, yeah, looks like R5 too. Okay, C2, oh, D1, the diode definitely has to be near here too. So right now I'm just sort of tossing stuff in I'm just sort of binning things in sort of their general area here. I kind of want to go back and double check that R5, yeah, R5 is on that part, yeah. So actually I want R5, R6, and C4 over there. R6 and C4, okay. R5, R6, and C4, okay. Well, that's all the junk we got to get in there eventually. Looks like we got to get C1 in there also. Boy, that one's going to definitely be a lot bigger than the other one. So this guy is going to be, of course, the pot. So C3, and then so we got C3, the other pot, and C5. That's about it. Stop doing that. So C3, C5. Okay, so it's mostly everything crammed in here. I didn't really recognize that before I started. That actually might change kind of the way that I space this all out. Probably definitely will change the way I space this out. So let's go back to our 100 mil grid. Okay, looks a lot better to me. Okay, so now let's get these, we kind of have sort of moved these guys into place. Now let's get a little bit finer movements here. So so especially with op amps, I always like to know which side of the op amp these things should be on. And you know, usually which side tells you which, the way these op amps are packaged, you have one amp op amps pins on one side, the other on the other. So it's usually fairly easy to tell. So for this first one, we should have R1, R2, C1, R3, R4, C2. Wow. So R1 through R4, C1 through C2. And I like to rely heavily on pretty heavily on the schematic when doing this, because the schematic really tells us where these signals are moving, where the adjacencies are. So we can use air wires, but boy, sometimes we save ourselves a lot of effort if we just sort of route it in the direction that we have here. So our signal's coming in initially through C1, so we probably want C1 to be kind of close to our signal side of things, like right here-ish. We also want this thing not to be ugly. We want to keep this ordered. So an orderly board is not, it's not just a matter of sort of having it look nice. It's also a matter of the more orderly you can make this board, the more you're going to decrease your chances of putting the wrong part somewhere or of not being able to easily debug this later. And actually, we'll probably go back later and do test points. But probably not for this video because I got to pick up my daughter. So C1's coming in, then we hit that. Oh, then we got R1 as our pull down. Oh boy. R1's our pull down here. So R2, so the diode's on the output. Diode's on the output. Of course, we gotta have that pot wired in there. R2 is our feedback, so R2 should be in pretty dang close to here. Then R3 and R4. And both C2 and R3 tied to ground. So what I'm doing now is I have, and you see this a lot with op amps in particular, quite often you'll have this sort of quad of, when you have a RC networks, either in the feedback loop or in the, connected to one of the pins of the op amp, it's very common to have 4 components or so that are all connected there. And it's not always clear exactly what the best orientation is to make sure those stay connected. Usually it's good to just kind of see, if you can follow what you have on the schematic. So in this case, we have C1 and R1 connected to that positive pin. C1 and R1 connected here just fine. Then we have, of course, that little connect out to that pot. Then we have the diode. On the other side of the diode, we have a connection to R2, R3, and R4. So we should have basically that one side of R2, R3, and R4 all connected to the same node. So let's go back. R2, R3, and R4. Looks like yeah, so we might want to, so that's that net D12 here. So we might want to kind of rotate this guy just to make sure that that net D12 is sort of all connected like that. And that should work okay. And then we'll, and you know, all the time you got to redo these later on. C2 should be connected to the other side of R4. So, you know, maybe it's better to move C2 over here. So we'll keep that like that. So we still have a, all these nets have to be connected. That's still fine. But this guy can be like that. Maybe I like that a little bit better. Maybe I like that a little bit better. I think I do. Okay. Yeah, that's all okay. That looks pretty good to me. We might want to rotate this guy. Looks good. Rotate that diode. Perfect. Okay, and now let's do the other side. Let's go to the other side. So the other side of this op amp is going to be, remember, it's going to be this guy right here. So we have R5. Now R5 is still going to connect to this signal that was coming off this C2 cap, so that's something to keep in mind. So we have that this net C2 underscore 2. And that net C2 underscore 2 is still going to be that's going to sort of connect over to the other side of our circuit. I still want to keep this resistor over here, and I know eventually, I don't have it down here, but I definitely want to have a test point on this node, so I'll add that later. So I just know that, yeah, we're going to have, you know, we're not clustering this signal too close together, so this C2R2, this net C22 is going to, probably should give it a better name and a test point, but it's okay if there's a long trace here, because there's probably going to be a big fat test point here eventually. Okay, so then we got, that's, so R5, and then on the other side of R5 we have C4 and R6, both connected to, they're all connected to the same node. So, and I'm not worried too much about the annotations right now. I'm not too worried about those annotations yet. So this is all looking pretty good right here. Feeling pretty good about this. Okay. So that side I'm going to call good enough. I might, you know, just for housekeeping here, kind of make sure these guys are aligned. Okay. Now let's go over to this op amp over here.
How's it going, Mr. Lund?
It's going good.
What did class today?
Yeah, we got class. Yep.
Hey, tell your students from last quarter to take their lab notebook. Except for Josh. He's got his.
And don't tell me.
Tell Nolan
Oh.
to take his lab notebook. Oh, hey!
Okay, how's this looking now? It's looking pretty good. Okay, so, and again, all we're trying to do is we're just getting everything in place. So we're going to route this all later. We're just wanting to get sort of everything just sort of roughed in right now. We have these, I'm going to go back to a grid spacing, and again, just hit G for grid spacing. I'm going to go back to 100 mil grid spacing to get these headers in place, just because I really, especially with headers, I like to have these on a grid that can that's going to be breadboard friendly, so just on a 0.1 inch grid here. So I feel pretty good about how this is structured right now, at least for getting everything roughed in. So I'll probably start wiring, and again, when you start wiring, you know, things don't typically always stay wired the way you wanted them to be wired. So, but we'll see what we can do with this guy. So I'm definitely going to do a ground plane for this. So we're definitely going to ground plane, probably ground plane top and bottom. So I'm not going to worry too much about ground signals right now, but what I am going to worry about is getting these plus 12 and minus 12 and the 5 volt signal routed here. So I'm going to start on the outside. On the outside I see a plus 12 and a plus 12 over here, and it looks like that guy can pretty much just cut all the way around all of these. So so we're going to begin the routing with make sure we're on our top layer. Make sure we actively route connections. So no reason to have this guy be thin right now. So we're going to switch this to, hit the tab, switch it to, you know, there's not a lot of current carried by this thing, but it doesn't hurt us to have it kind of a little bit bigger. So I might do something like 40 mil, which is plenty. And my grid is way too coarse, so now I could have routed this on either side, this connection. Doesn't really matter. I usually like to keep things on the top layer if possible, but they don't have to stay on the top layer, especially in this case when we're really connecting a through hole to a through hole. The benefit of doing this on the top, though, is this signal is going to have to connect to this, it is going to have to power this op amp, so it's going to have to connect to this pin. So it is one thing if we do route it here, it's easier to, from the top, get to that top of that surface mount connection. In general, with surface mounts, they are, you know, they are top routed, so gotta deal with it. So we gotta, let's start with this. Let's get this 5 out of the way. The 5 doesn't route to the other side of the board, and it looks like the 5 doesn't route anywhere, which is a problem. That is a problem. That means that is bizarre. 5 volts here, and oh, you see what we did? We called it plus 5 here and 5 volts elsewhere. Well, so you know, I gotta double check. Okay, so yeah, you don't want to just blindly route and say, oh, that's a magical connection that doesn't need anything connected to it.
Okay.
So, Tim has this old oscilloscope. I'm trying to see if it will still work. But it has this stuff connected to that. So I'm not sure. We don't want to like plug it in if it has stuff oozing out of it.
It looks like they just kind of glued that.
Oh, it's just glue?
Looks like it.
Okay. This one's a little bit more dicey. You know, I might actually route this guy around the back. Now, we generally want to be careful when routing these like this because we want to make sure in the end we have a ground plane that's fairly close to here. Definitely want to make sure we maintain a close ground plane. You know what? Actually, this is probably a good candidate for routing on the other side, in fact. So, okay, fair enough. Pulse out. That's going to be a signal route, so let's not worry too much about that. Mag out. That's also it, and the real last one's ground. So we'll leave those power rails like there. One thing I don't like about this right now is how this trace just cuts all the way through the bottom, and what that means is that when I have a ground plane on that bottom, it's not going to be doing much good on either side here. But we'll see. It's just something to keep in mind. These long traces, you know, cutting big swaths across your circuit on both the top and the bottom layer is usually dangerous, so there's a good chance I'm going to have to undo that later on. Let's start doing some small ball routing here, though. So let's start doing some top layer routing. It's a little bit too big for signals. We'll just do a 12, which I find to be a reasonable signal value. Sometimes I start with these little connections. I just kind of start with the little guys that are close. And this is a part where I do kind of want to move these annotations out of the way. Move these names out of here.
Yeah, it's only got it. Some using at the back. Cool. Right.
Don't really need to connect the grounds. Okay, let's start doing these pins. I don't feel good about routing that guy yet. That was an ugly corner there. Now you see, we start routing this plus 12. Altium remembers that the last time we routed this signal, it was a big trace like that, so it's going to keep it like that. We don't need it to be quite that ridiculous. That's our ground. A little worried about routing this guy. Ugh, yeah, that was that. That was that beastly one. Oh, we're gonna punt. We're gonna do everything else, and then we'll get to that guy. Let's get our input signal here. Now you might notice I'm using kind of a coarse grid here. That's for a reason. I like to keep things as clean as possible early on. There's no reason to sort of do a fine, super fine resolution on a lot of these routes. So we're not gonna. So let's see where this guy goes to. I don't exactly love that. What I'm going to do is okay. So now I'm going to route this guy first.
After these left, you have to bring back all components.
Oh, yeah.
Right now they're all.
Okay, cool.
I need some of those coupons.
Coupons on.
Coupons or coupons?
So this is the price we knew we had to pay. We got to connect this guy.
Borrow this. Yeah, it's that one again.
We really should change the rules to fix this. So. That's okay. Looks like we're gonna have to change the rules though. So now we're gonna route this signal in. I think the only signal left there is ground. Yeah. Ground. Looks like we got this net too. Okay, so I encountered a situation where I got to cross over these signals, but these signals are placed arbitrarily. So I think what I'm going to do instead is back to my schematic. And do that. And we can do that. If our signals are just being sent out, we don't care about the order, might as well make it easy on ourselves. So. So we've kind of created a condition where I'm guessing this guy's going to be tough to get a ground signal to. That's alright, we can plop down a via there. All ground, all ground, all ground, okay. So I think we got everything routed now, with the exception of our ground connection. And we did a pretty good job of keeping it up on the top layer. That's not bad. Okay. Oh, I gotta run off to class, but we will be back in just a jiffy, which for you will be instantaneous. Okay, so we're trying to get that ground in place. So the one, I'm looking at where my grounds are, and I'm not too worried about them. With the exception of, I think it might be easy. So this guy, there might be an issue getting ground to him through here. So the good thing is a couple of these that are pretty easy to just sort of move around some routes right now to help get a ground signal in. To help kind of move a ground signal in there without it creating a big hassle. So we're going to give that guy some space so that ground can sort of work its way in there with a nice fat trace. These grounds, these grounds are going to be isolated where they are now, but watch this. If we move this trace over to here, alright, so check that out. Now, right now this ground connection here is going to be able to get in there just fine. We still should. How about our ground getting in here? Well, we can move this guy over a little. I don't like that. Change my grid, do something a little finer. There we go. Give that space to let the ground in, and we might add a couple vias later on to connect these. We'll sort of see how it's looking after we're done with these planes. Oh, and I also want to get ground into here. So to get ground into here, let's just give this guy a little space. Perfect. So now we should be able to get a little more ground in there. Yeah, and we can even, you know what, we can even I'm making a mess here now. Yep, gone too far. Okay. Let's get that ground on that side of that route. Beautiful. Beautiful, okay. And maybe we can give these guys a little more breathing room. Good enough, okay. Okay, so let's get those ground planes in there now. So I might as well now just define the shape of my board, and then I'll just use that board shape as yeah, and that'll be fine. So let's look at let's do our board shape. So we had this sort of initial board here. I'm just gonna go ahead and delete that. I kind of know I feel pretty good about this shape here right now. Of course, I could tighten all this up if I wanted to. I don't really care too much about it though. So let's place. We'll do mechanical 3. Place some mechanical 3 lines here. So we're gonna go out to. Let's do a 50 mil spaced grid here. It's looking good. Okay. Okay, so that's our nice board outline. We can move some of this stuff around later. Yeah, we can move some of this stuff around now, actually. Okay. Actually, you know what? Yeah, that's fine right there. Okay. Okay, so now we're going to make our board. We're going to define our board based on the shape. I'm just going to right-click, find similar objects. We can also just look at the connected ones. So we're going to do all tracks in a mechanical 3. That selects the board outline. Now we're going to do tools. Design board shape. Define from select objects. Boom, look at that. Close it up. Let's take a look at 3D view. It's looking good. Looking pretty good. Okay. Alright, looking great. Let's go back. Let's do a plane. So let's do tools, polygon boards, polygon manager. Create polygon from board outline. Top layer, top layer. So we're going to do ground net on the top, ground, pour over all same net objects. I like to remove dead copper just so I know where it's plain and where it's just for show. Then let's do create new polygon from board outline. Ground bottom. Okay. Alrighty. Now we're going to apply these polygons, looking good. We can look at them both from here before. See, that was what I was talking about. You run that line all the way through here, and it kind of bites you a little bit. Bites you. We want to make sure that's not a critical pathway for our ground. I don't think it is. But we'll see. It may be. It may be a critical pathway. If that is a critical pathway, there's other options that we've got here, but yeah, this one too, it looks like there's not a lot of connection between the top and the bottom half here. Yeah, there's pretty good connection here between the top and the bottom half. I'm not too worried. So okay, we'll click OK there. So sometimes what we can do, so now we got our ground planes. Let's take a peek. Looks good with those ground planes. Looks great. So sometimes what we want to do is if we want a really good ground plane, and we kind of do in this case, we want to tie the top and bottom together. So clearly the top and the bottom are tied together right here. So we know we got good connections here, but I'm worried about the connection between ground here and ground here. So if we go back up to here, I see two sort of good spots to do this. So we'll probably just put a ground connection here, and then a ground connection up here, maybe a couple of them. Maybe a couple of them. We're going to hit tab and make sure this guy is specified as a ground. Okay, I kind of still like this grid spacing here. I kind of like that we got a that's all okay. Okay, let's go back and look at that. So let's look at the bottom layer. So now we do have a good connection between this top bottom layer and this bottom layer through this sort of copper connection here. And you know, it's not a huge, you know, this is obviously very fat, very low resistance here. Sometimes I get a little paranoid that, you know, it's fine, we'll leave it like that. See if there's anywhere else where our ground gets kind of wasted a little bit here. No, we got a pretty good ground connection from here to here. Very good on the other side. Are there any little windows where our ground gets pinched off? Pretty good ground connection in here. Might be better. Add a couple. Might be good to add a couple ground points here too. Yeah, we don't want to add a pad. We want to add a. Yeah. Okay, let's look for any stranded grounds now. That guy's good. These guys are solid. These are pretty solid through there. It's good. Good, solid ground. Okay, that was most of that was probably completely unnecessary that I just did, but whatever. It's nice. Better. Doesn't cost us anything. Better than not having anything there. So let's go back to our 3D view. Oh, and immediately I hate that. Those aren't tinted. So let's go back. Right click one, find similar objects. CSA apply. Tentum. Okay. And we look like we are.
There's a fire extinguisher on top.
Rectifiers.
The
Full wave rectifiers from the wall.
Okay, we are almost done here. All we got to do is move around the annotations here. So, and these annotations are currently big. And actually, to do the annotations, I'm going to switch to top overlay just to make sure I grab that. Switch to a finer grid here. C2, R4, R3. Not a good place to put R2 here, so sometimes when you can't fit it in there, you'll just sort of do something like this. You'll just kind of first of all, what we should do is shrink all of these. Find similar objects. Say, change these to 40 mil, 6 mil. Okay. And now they should fit. So, oh boy.
So we're trying to put some nuts on the screen. It has this going on, this like brown to be and also brown to also be red. And
So still doesn't really fit
this
there.
is supposed to be for like
Sometimes what you can do is just put them next to each other like this to make it clear that they're ordered like that.
This just doesn't look right. So it have like ground.
Diode. C1R1.
This is for the. This was similar to the one that you had assembled for the tower.
Well, let's see. So
R6.
Yeah, I guess the bridge to go on.
R5.
this is
C4.
Isn't that weird?
U2. Hey, hey, hey. Okay. C5. C3. Oh, these guys fit here now.
But it seems strange that just to mess up because these are identical on either side too. Like it's like they would have had to mess up on the fourth.
That probably is like probably
No. I guess, or did you set up the towers or the LCD screen and then that bit?
Which one?
The tall
Eight
tower.
sixty five?
Yeah, it's the bad one.
Looks pretty good.
Are you sure that's
Looks pretty good. The only thing left to do
Well, I'm not
is
sure.
add
It's just what the data shows.
signal silk screen here.
It's just what they edited.
Let's get a little crowded. So we'll skip that part of the video. We'll add the silk screen here and then it's good. And we're done.